Hi everybody. Today we will talk about the electric potential and potential energy in PHYS102 course. Okay, so the first thing we will start with is that if a particle goes from one point to another point, say A and B, okay, on a path, doesn't matter what kind of path we have, okay, doesn't matter what kind of path, okay, the object is moving. In PHYS101, we have seen that the mass m moves at a distance from A to B, but in our case, we will also have the charge, okay, for this mass. So this charge can be positive or negative, and it moves from one point to another. Probably there is some electrical field like that, or maybe magnetic fields. We will see the magnetic fields later. So if the charge is moving under the effect of this external electric field, some kind of force is exerted on this charge. And if the force is given by F, it is Q times E, as we know. So what about the work done by electric field? What is that? Because when the charge moves from one point to another point, this electric field will change its direction and maybe it will accelerate or decelerate. Okay, so it will just create the effect. So if the effect is created, it is created by the electric field. So what is the work done by this electric field? Okay, not external, somebody is pulling or pushing or something, but the electric field is just changing its motion. So in this case, the work done is just force times the distance, or dl, let's say, some kind of distance. But these are all vectoral quantities. The force is given by that, and dl is the distance, okay, small distance that we consider along the path. And the force is given by this expression. Okay, so now, if this is the dot product, it is written as F times dl times cosine alpha, where alpha is the angle. If the electric field is this one here, is the angle between the two, for instance, here. Okay, so also we have to put the limits, because now the object is moving from A to B, so we have to put the lower limit as A and upper limit as B. So we just have to integrate, and we say that this is the work done from A to B. This is the subscript that we use, a little arrow B. It means that the motion is towards B from A. Okay, so this is the work done by the force. Actually, the force is created by the electric field. So don't forget, the forces are always created by some kind of fields. In our case now, it's the electric field. Okay, so now if we know that, so this is number one. This is number one. There are some rules about the potential and potential energy, as you see. Number two, okay, which is very important, is that if F is conservative, the force is conservative, then it can be written in terms of potential energy. U, potential energy. So if U is the potential energy, what is its units? Don't forget, potential is volts, but potential energy is joules. Don't mix them up. So we use capital letter V for potential, but for when we use U, just like we have done in PHYS101, it means that it's just the potential energy. So of course there is a relationship between U and V, potential energy and potential V, as we will show. So if the object is moving from point A to B, then it probably has some kind of potential energy at point A, maybe even kinetic energy at point A, if it is not starting from the rest, Of course, it has a kinetic energy because when it's moving, there is a velocity, right? Like that. So now at point B, the object or the charge has not only potential, but also kinetic energy, okay? So it may have kinetic energy at point B, and obviously the velocity can change. Okay, in this case, it's changing at least the direction, okay? So this is the velocity VV. As you see, there are some many factors that we have to consider. So this charge is moving from one point to another point under the effect of this electric field, which produces a force on this charge. And because of the fact that it may have some velocities, of course, if there is a motion, there is probably some velocity decreasing or increasing. It should have a kinetic energy, and also it may have a potential energy, okay? Potential energy. So not necessarily, okay, they should have both of these kind of energies, depending on the cases. So now, usually when we have delta U, for instance, it's always U after, okay, minus U before. So this is change in the potential energy, change, okay, in potential energy. So in our case, delta U is just because after is B, because it's happening afterwards. The initial case is A and the later case, okay, the case B. So this is written as UB minus UA. But if this is happening under the normal circumstances, okay, the potential usually decreases, and in this case, the potential at point A is usually greater than potential at point B. Just like the object falling, okay, down from the top of the mountain. Okay, here it has a greater potential energy. Okay, B at point B from A to B. Okay, so UA potential energy here greater, but UB is very small or zero even, because the potential energy for falling objects was mg times y, where this distance is y. As you see, when y reduces, the potential energy reduces. So it means that if the particle has a higher potential, it will lower its potential, because this is how the nature works, right? So all the particles and all the charges and everything, all the matter in the universe, try to reduce its potential energy. This is how they move. So if the stone is left free from the top of the mountain, it will just go down to lower its potential energy under the normal circumstances. So that's why usually potential energy afterward is smaller, okay, than the initial potential energy. This is the usual case. So in our case also is like that, okay? So we are assuming positive charge and electric field is in this direction. So both DL and electric field are in similar directions, not necessarily the same, of course, not opposite, but in similar directions. In this case, under the normal circumstances, we can say that the potential energy at point A is greater than the potential energy at point B. But delta U is defined like that. So, but we can write it like this, minus UA minus UB, okay? We can do that. So, basically delta U can be written like that. So it doesn't matter how you write it, okay? So now what we would like to say that this WAB, which is the work done by the electric field on this charge, is related also to the change in the potential energy. So WAB is equal to minus delta U, okay? So this is very important. So you saw this in PHYS101, okay? So the reason that we write it like that is because we will come to the conservation of mechanical energy. In this case, we will also have the change in the kinetic energy, but when we combine the two quantities, we will have the conservation of energy, okay, mechanical energy. So how do we do this? Okay, the reason that we have written the change in the potential energy like delta U is because this work done is also equal to delta K. So the work done, if, as you see, delta K is KB minus KA. So if a work done on the object, let's use our logic, okay? So don't forget, the object is moving from A to B. If the work is done, work done is positive, because it can be negative also, right? Depending on the differences in the potential energies and kinetic energy. But if the work done is positive, then we expect that it speeds up, right? Then KB should be greater than KA, okay? But we will see that it's just the opposite for the potential energy. So in this case, if W is positive, okay, delta K is positive, but delta U is negative. It means that the potential energy reduces, but the kinetic potential energy reduces, but the kinetic energy increases. But total energy is constant. This is really minus delta U, which is equal to also delta K, okay? So if these are equal to each other, then if you put, just ignore this part, if you put this delta U to the other side, we will have 0 equals delta K minus plus delta U, because this was minus. When you put it the other side, okay, it will be positive. So we don't forget, we are not considering this case, we just consider this part now. Okay, now so what is that? So it's just a delta kinetic energy plus potential energy, which is delta total energy or total mechanical energy, because there are different energy types. Maybe if there is a chemical energy from this point to that point changing, or maybe even nuclear energy or some kind of other gravitational energy or something, then you have to also include those potential energies, okay, into the expressions. But in our case, it's just a mechanical energy, okay, which consists of kinetic and potential energies only. So if delta E total is 0, then it means that E total at point A is equal to E total, okay, at point B. So UA plus KA, which is equal to, okay, UB plus KB. So this is the expression that we have to consider in solving these, these problems. Okay, now this is the conservation of energy, by the way. So it's very important to understand how this expression is used. So now, don't forget, we are dealing with the charges and also electric fields. So we know that the force on the charge, okay, let's draw some kind of pictures here, okay? So suppose that is our y direction and the motion is only in one direction. So we have a plate, let's assume we have a plate which is positively charged, okay? Below we have another plate which is negatively charged. Obviously there is an electric field between the two, okay? So electric field is downward in negative y direction. And let's assume that point A is this, point B is that. So the charge is moving from point A to B, okay? Not necessarily in straight direction. Maybe it's moving like that and coming to point B, or maybe it's doing this, coming to B. Different paths, as you see. So these are all different paths. Okay, different paths. So as you see, the work done for conservative forces, okay, for conservative forces. So the electric force is conservative, as we have said, okay. The work done is independent of path, but only dependent on initial and final points. So it doesn't matter how the charge is moving. The charge is moving in this direction or in this path or maybe straight. Doesn't matter. Okay. So the work done is found by with the same expression. So what about the force because of this electric field? Don't forget, the force is equal to minus Q EY. Okay, Q EY. The reason that there is a minus sign is because force is in negative y direction. Okay, the force is like that. So we're not writing this as a vector form. If we write this in vector form, okay, we should have done like F equals QE. So this is still the same expression we are using, but E is negative, in negative y direction. That's why we have this minus sign. So the force is there. What about the potential energy? But the potential energy is, remember that potential energy is related to W, but W is force times the distance. So in our case, it's just this times the distance, okay? So the potential energy is given by just Q, okay, Q times EY times the distance, which is Y. So the distance it moves, okay, the difference between the 2 points is given by Y. So now we have the potential energy, okay, the potential energy is just given by Q E times Y, okay, Q E times Y. So now let's do the work done on this charge, okay. So we will handle the minus sign. I will just tell you how it is done. Okay. So so now suppose the charge is doing this kind of motion. So let's draw it here, okay, to make the explanations clear. Okay. So this is our y direction, always towards up, but the charge is moving from A to B. So it means that y is reducing. Okay, the charge is moving in this direction, either in this path or maybe like that, doesn't matter. Okay, so work done, okay, work done on charge by electric field. Of course, electric field is in this direction from always plus to minus. Okay, by the electric field, okay, is given by minus delta U, which is equal to minus UB here is positive, and it is QE times Y. Sometimes it's positive, sometimes negative. In this case, the potential energy is given by this expression. As I told you before, it can be negative or positive, but we chose Y equals 0 here so that for positive Y's, positive Y values, the potential energy is positive. In this case, this Q, okay, E times YB minus Q E times YA. So if you just factor Q and E, okay, we get, okay, Q times E times YA minus YB. We have this case. We use this minus sign here so that it made YA, the coefficient of YA positive, but the coefficient of YB negative. So we have this expression. So when we, now, this is the change in the potential energy, okay, which is given by this expression. Now, this is the work done on the charge, but also it's equal to minus UB minus UA. Don't forget, delta U is always written like that. Okay, now let's look what happens. There are different scenarios because you may have not only positive charges, but maybe negative charges, but also the charge can move from point A to B, lowering Y, but it may move in opposite direction somehow, okay? Then everything will change, as we will see, okay? Everything will change. Okay, now, sorry about this noise. So now let's do normal case. Normal case. In normal case, okay, electric field is this way. The positive charge is moving downward, and Y direction is this. Okay, so now as you see, this electric field exerts a force in negative Y direction, but the object is going in the correct direction, okay? So in the direction of the electric field, the charge is moving. This is a natural case, normal or natural case, okay? Natural case. And then in this case, W is positive. So if we ask ourselves, is the electric field doing work on this charge? The answer is yes, or positive. You give positive answer for this. And the potential energy reduces, okay? Probably kinetic energy also increases, okay? But we're not getting into the kinetic energy business yet. So normal case is this. But now look what happens. This is case A. Case B, again, we have Y upward, electric field is downward, but the charge is moving now from from point A to point B. Okay, the electric field is downward, but the object is moving from A to B, but A is lower. Okay, again, our charge is positive. Now, as you see, this is not a normal case, because normally, if there is an electric field downward, the force on the charge would cause the charge to go downward, but now the charge is going upward. So it means that something else is doing the work. So if we ask ourselves, if the electric field is doing the work, the answer is no, or negative. So W is negative. Do you understand the difference between positive and negative? So if your answer is yes, the W is positive, but if your answer is no, the W is negative. So in this case, because normally the electric field would do the work if the object or the charge is going downward, because it would be the force, okay? It would be force that governs the motion here. But probably here, in this case, it's opposite, because maybe there is another force which is greater than electric field, so that the object is moving from point A to B, increasing Y distance, which is not the normal circumstance. In this case, if we ask ourselves, is this electric field doing the work? The answer is negative. No, it means W is negative. But now what happens is that the potential energy increases in this case. The potential energy increases. So now, if we consider the negative charge, for instance, negative charge, suppose, again, we have electric field, Y is again in this direction. So this is different case. Let's just put these in, okay, regions. So in this case, electric field is again downward, okay, the same. So this structure doesn't change. But now let's have a negative charge, okay? Negative charge is moving from A to B, A to B, okay, like that. The charge is moving. So this charge is moving downward. Now, is this a normal case? It is not a normal case, because normally, if electric field is downward, and if you release this object or charge, okay, if you release this charge, sorry, somebody is trying to get connected. Okay, if you release this charge, normally it would go in upper direction, because electric field is downward. The force on the object, remember that F here is just QE, okay, but Q is negative. So the force and the electric field directions will be in opposite directions. So for this case, F equals minus QE, okay, in this case, for this case. So it means that normally, if you just release this charge, it would go upward instead of downward. So it's not a natural case. If it is not a natural case, the work done on the object is positive or negative. The answer is negative, because something else is doing the work, or maybe another external force which is causing the charge moving in opposite direction to the direction that this electric field would cause. In this case, the potential energy, of course, is increasing. Okay, so as you see, the potential energy increases or decreases depends on the work done, okay, which is positive or negative. So it's always opposite. So if the work done is positive, the potential energy decreases. If it is negative, it increases. So of course, normally, if the charge is moving, this is case C, if the charge is moving in opposite direction, W is positive, but the potential energy is reduced. So this is very important to understand the sign of the work done on the charge or objects actually. Okay, now let's consider the case where suppose that this charge is moving under the effect of electric field, but this electric field is created by another charge. Okay, in this case we consider two charges. So there are two charges. So this charge plus Q, okay, is creating this electric field in all directions, as we know. Okay, so electric field will extend in the space. So this electric field goes everywhere. Okay, but we're just drawing this part. Now let's assume another charge, which is Q0, moving from point A to point B. Okay, Q0, which happens to be positive. Okay, if otherwise it's specified, we always assume that the test charges are always positive. Anyway, so if we measure the distance from this main charge, which produces electric field and fixed, this is fixed, by the way, fixed, but this is not fixed. Q0 is not fixed. If both charges are not fixed, then the problem would be very complicated. But in this case, we fix this charge and we create these electric fields, and the small test charge is moving from point A to B. Okay, and the distances are measured now, RA here, and the other distance, the final distance, is just RB. Okay, if we have to put the vector signs, but we know that everything is in radial direction, so not necessarily we will use the vector sign afterwards. Okay, so the distances at an earlier distance is A, and distance at a later position is just RB, RA and RB. Okay, now what's happening? We know that at each of these points there are Coulomb forces. Okay, Coulomb forces was given by, remember, K, Q times Q0 divided by the distance square. Okay, Q is the charge which creates electric field, and Q0 is the charge which is moving from one point to another point. Now you can ask me this question: if this positive charge is creating electric field, what about this test charge? Is it not also creating electric field? The answer is yes. Of course, it's also creating its own electric fields. But now we are examining its, okay, this is the electric field created by this charge, but it's also in the motion. So this self-electric field doesn't cause any force on itself. Okay, this is the reason that we consider only external electric field. This external electric field is probably coming from a flat surface, just like this case, or just from a point charge, or some other force. But now, in order to understand the forces between the two charges, okay, this is the expression we use. Now, look what's happening. So plus Q is here, and Q0 is there, and this is the force direction. This is this force here, F, okay, and for this charge, okay, test charge, the force is this way, or the other way, okay. In our case, because both of these forces, both of these charges are positive, we understand that this is not an attractive force, but repulsive force. So the direction of the forces are going to be away from each other. Exactly the same forces, okay? The same force here, the same force there, okay? Now, because this positive Q is fixed, it's not moving, but this is moving. So the force doesn't matter. So if the force is exerted on Q0, the same force is exerted on Q, but Q is fixed, plus Q is fixed. Okay. In this case, the force is given by this expression where the distance is given by R. This is Coulomb's force that you learn in high school. Okay. And now we would like to do this calculation from A to B. What is the work done by the electric field created by Q? Okay, how can we calculate the work done on the test charge, which is Q0, from RA to RB? The reason that we use R is because this is spherical symmetric case, and now we write Fr F times dr, but since dr is also in the same direction of electric field, as you see, this dr is a small distance here. This is dr. The small distance dr is also in the same direction with the electric field. So F dot, we can write it like that, Fr dr, okay, like this. So then this is equal to, okay, let's put the limits from Ra to Rb, from Ra to Rb, okay. Now the force is just K Q Q0 divided by R squared and dr, as you see. We have to integrate this function. This is not a difficult integration because all these things are constants. You can take them outside, and then WAB, okay, is written then K Q Q0 integral 1 over R squared dr. But this can be written as K Q Q0 R to the minus 2 dr, as you see, okay. So the exponent on R is just 2 with a minus sign. So to integrate these kind of this power functions, we increase the exponent by 1 plus 1, we add 1 to the exponent and divide by the same number in the exponent. So the result is very simple. It's very interesting. Okay, very simple integration. So it's just R to the minus 2 plus 1 is just minus 1 divided by minus 1. Okay, so exactly the same thing is written downward. So it makes it minus, and now the limits are Ra and Rb. So if we now put this expression minus K Q Q0, okay, now R to the minus 1 is 1 over R. Don't forget, okay. So this is why I'm writing this as 1 over Rb upper limit, okay. I put this minus sign here, as you see, minus 1 over Ra, okay. Now look what's happening. Which one is greater, Ra or Rb? Rb is greater, but 1 over Rb is smaller than 1 over Ra. So this expression is negative. But if you put this minus sign here, then it can be written as K Q Q0, okay, 1 over Ra minus 1 over Rb. So this, don't forget, this was del WAB, but it is equal to also minus delta U, because this WAB is equal to minus delta U. So it means what? This is also UA minus UB. Don't forget, delta U is always UB minus UAB. Final minus initial, but if there is a minus sign, it's written as UA minus UB. But the right-hand side is this, as you see. If you multiply these, common factor, the expressions on the right-hand side will be K Q Q0 over Ra minus K Q Q0 over Rb. Wow, it's interesting. We have now the difference on the left, and we also have the difference on the right. So this must be equal to this, and this must be equal to that. Very simple. So this shows us that the potential energy is K Q Q0 over Ra, just like Coulomb force, except instead of square on the denominator, we have just R on the denominator. So now what we learned from this exercise is that the potential energy is given by K Q Q0 over R, not R squared, just like in Coulomb's case. So now the potential energy, this potential energy, so if there are two particles or two charges, you just measure the distance between the two charges and just get the potential energy. Don't forget, the unit of the potential energy is joules, but the unit of potential is volts. This is second reminder to you. Don't forget. Don't mix up the potential and the potential energy. Okay, so now what we would like to do is that we would like to consider a few charges together. So if we can calculate the potential energy between the two charges by just measuring the distance between them, then we can put a few charges together and measure the total potential energy until they move, of course, if they are fixed. Once the charges start moving, okay, then the problem is more complicated. This is the reason that in this example, we fixed this charge. We didn't allow this charge to move, but only this charge was moving. But if this charge was also moving, the electric field would also change according to its position. Okay, so the force from A to B, the electric field would change, and the force wouldn't be conservative in this case. But for the fixed cases, it is conservative. So the direction of the electric field would change if this moves, for instance, this way. Okay, so this is not the case. So now we learned how the potential energy is measured if there are a few charges together. Okay, so now having stated that, we would like to now solve some examples about how we can calculate the potential energy if there are more than one charges. So now let's look at the graph of this potential. Don't forget, the potential energy between the two charges is K, Q, Q0 divided by R. Now let's graph this, okay, as a function of R. Now, these two charges can be positive or negative, as you see. So if both of them are positive or both of them are negative, U is the positive, right? U is above this radial axis. So, but now when R gets closer to zero, the potential energy blows up. So it's like a singularity. However, it's not the case, because these charges will have some sizes, and the distance between them, which is measured always from their centers, will never be able to be zero. But when they touch each other, it will be a smallest distance possible, okay? Because they have some sizes. So don't worry about R being exactly zero. It never happens. But when R is very small, the potential is extremely large, okay? But now when you get away, when these charges get away from each other, in other words, this charge gets away from this, the charge which produces electric field, then the potential energy of the two charge system reduces to zero. But it becomes zero at infinity, as you see. It's a long-range interaction, long-range effect. So unless the second charge goes to extremely far away from this charge, then the potential energy still can be measured. So it may be extremely small, but not zero, okay? So now, but what is, so Q0 plus plus or minus minus. Okay, in this case we have this. But if one of them is negative, look what happens. Okay, so now here Q and Q0, maybe this is plus and this is minus, or this is minus or this is plus. It means that they have opposite charges. In this case, the potential energy should be negative. The product of positive and negative gives you a minus number. So, but we should have also the same case. But now what happens is that this graph becomes like that. Okay, as you see, negative very high potential we have, but almost zero potential when the object is totally too far away from each other. This is the case in the atoms, because we have a positive nucleus, and then around there are some electrons, but electrons are negative, right? So the potential energy between the two systems, say this electron and this nucleus, is like that. So now the minimum potential is when this electron is nearest to this nucleus. This is the reason that, but minimum potential energy means maximum kinetic energy if the energy conservation is holding. So in other words, if there are electrons at different orbits that are moving around the nucleus, so the ones which are nearer to the nucleus has lower potential energy, which is negative potential energy, by the way. It can never be positive because this is plus Q, very big charge, but this is one of the electrons which creates total charge, negative charges. So if this electron is nearest, then it's moving faster and faster, but the potential is negatively minimum, okay? So it's just, it is reached the minimum value. But now what happens is that if you remove this electron away from this atom by giving some heat or maybe photon or something like that, this electron goes away and the potential energy decreases to zero from negative values. So the magnitude decreases. So it means that they are not connected anymore, okay? So, but now what happens is that the kinetic energy starts increasing once the electron is, because the potential energy decreases negatively, but the kinetic energy, okay, kinetic energy also decreases until you give some external force on the electric field electron so that its speed increases. So now, as you see, the sign of the potential energy really is telling you how the system is being arranged. Okay, we cannot really do the simulation for the Earth and the Moon, because Earth has some kind of magnetic field distribution, but the Moon is totally cold planet, so we don't have any charge interactions or something like that. Besides, we have gravitational forces which are really causing all the motions between Earth and Moon, and also the other planets, and also stars and moons and everything. So we are just dealing with the atoms now. Okay, now it's really interesting. The timing is okay, because now we can start with solving some interesting example, atomic kind of example. Now we have a positron. Okay, we have a positron which is moving. Positron is exactly the same as electron, but which has a positive charge instead of negative. Electron is a negative charge, but this is positive charge. So the mass of the positron is exactly the mass of the electron, which is given by 9 times 11 times 10 to the minus 31 kilograms. Okay, very small. As you see, if one, look how much smaller it is. 1 kilogram is just 1 times 10 to the 0, but this is 9 times 10 to minus 31. It's extremely small, smallest unit of the mass. This is what we accept, right? Electron is the smallest matter. But we have seen that also electron is made up of some other subatomic particles, but we're not getting into these details. So what about the charge of the positron? It's also the charge of the electron, which is given by just 1.6 times 10 to the minus 19 coulomb. Okay, these are the constants that we give. Now let's assume that a positron moves in the vicinity of an alpha particle. So this is an alpha particle here, and electron is moving like that, maybe like this. But in order this system to work, don't forget, you have to keep the whole system in vacuum. In other words, you have to reduce the pressure of this this boundary. Okay, this room can be stainless steel or glass or something. You have to suck the air outside and make the pressure extremely smaller, in the order of like 10 to the minus 9 torrs or something like that. Very small pressures. You can repeat this experiment under the vacuum. Okay, but usually in the atmospheric case, the pressure is, in terms of torr, is about 760 torrs. So maybe 800, maybe 1000 or something. So in the order of 1000, okay? But now, like in the order of 10 to the 3, as you see, you have to reduce the pressure to 10 to the minus 9 torr in order to do this experiment. So always keep this in mind. So you need to draw a boundary for atomic kind of experiments. Otherwise, you cannot do this in atmosphere, in the lab, in the room. You cannot do that, okay? So always keep this in mind. And this is technologically extremely difficult. But there are some people in this country who are working on positron and doing these kind of experiments. One is my friend in, Professor Uğur Yashi in Marmara University. Okay, he's doing the experiments with positron. Anyway, let's now we know that this experiment is being done in vacuum. Okay, so now electron is moving. This positron, actually positive electron, okay, is moving in the vicinity of this alpha particle. This alpha particle charge is plus 2e, okay, and here is just plus e, okay, the charge of the positron, okay, plus e plus 2e. So it's a helium particle which has lost 2 electrons. If you get 2 electrons away, the total charge of the atom becomes positive, and then since 2 electron is just taken off, somehow giving some energy or something, the alpha particle is positively positively charged. And as you see in this case, both of these charges are positive, okay? So alpha particle is positive and also the positron is positive. So now we know that this charge of this alpha particle, which is Q alpha, is equal to just twice as much as this, 3.2 times 10 to the minus 19 coulomb. Okay, so we know the charge of the alpha particle, we know the charge of positron, which is the same charge as electron. Okay, now let's look. If you compare the masses of this helium, okay, this alpha particle is 7,000 times, okay, mass of positron. It's very heavy. Because this is very heavy, we can consider it fixed, okay? Because like if this is 1 kilogram, this is 7 tons. Obviously, it's not going to even feel this effect, but electron will feel it. So we assume that this is stationary, almost. So approximately stationary. So this is the alpha field, just like the fixed charge that I have described here, okay? Now, when the positron is 1 times 10 to the, okay, 1 times 10 to the minus 10 meters from the alpha particle is moving directly away from the particle with the speed. Speed is given. So this speed, so when the distance, let's put the electron here, when the distance between them is just 1 times 10 to the minus 10 meters, okay, 1 angstrom. Okay, then the speed is given as, okay, 3 times 10 to the 6 meters per second. So the speed is 10 to the, okay, 3 times 10 to the 6 meters per second. It's a huge speed. Don't forget, this is electron is moving in 1 second, 3 million kilometers, 3 million meters, or 3,000 kilometers in 1 second. So it's a huge speed. Yes. Can we get these kind of speeds in the vacuum? Yes, we can. Physically, we can do this. We can reach these speeds in laboratories by considering only the vacuum system, very carefully designed system. Besides, we have electron and positron producing things. Okay, now it says that the velocity given and the distance is given. Okay, so now it moves, this electron moves obviously here to point B. This is point A. In this case, the distance between the two charges is given as, okay, just RB is given as just 2 times 10 to the minus 10 meters. So this is RA. This is RA. So 2 different distances are given, as you see. Now, because they have both positive charges, okay, the electron will, the fact that electron moves away from this positive charge is natural. In this case, we can use the conservation of energy. So Ka plus Ua will be equal to Kb plus Ub. Okay, the conservation of energy states that the total mechanical energy at point A is equal to total mechanical energy at point B. Okay, so Ka and Ka is given, right? Because they give the velocity at this point, but they don't give the velocity. So they ask, what is the velocity here? What is the velocity at point B? So the question is, find the velocity at point B. Now, what we know is that we know the distances. If we know the distances, we know the charges, we can calculate the potential energies, okay, at points A and B. And also, we can get the kinetic energy at point A because the velocity is given, okay. Then all we are left with is the kinetic energy at point B, which the velocity can be easily calculated. So in here, we have to first find the kinetic energy at point B. So Ka is 1 over 2 mVa square plus Ua, but Ua is, don't forget, the potential energy between the two objects, between the two charges, which is given as just, okay, K times Q times Q0 divided by RA. Square or not square? Not square. Okay, don't forget the potential energy doesn't have any square here. So it's equal to KB, which we have to find, plus UB, what is K, Q, Q0 over RB. So if you put all these distances like this, okay, so how can we do this? 1 over 2, the mass is given as 9 times 9.11 times 10 to the minus 31 times the velocity square, but it's given as 3 times 10 to the 6 square, so it's 9 times 10 to the 12. Don't forget, when you square this, the exponent becomes twice as much. So 9 times. So when we multiply this, we get Ka as like 4.1 times 10 to the minus 18. What's the unit? The unit is, of course, joules, because it's the kinetic energy. Everything is in joules, 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 joules. Okay, good. So what about this? We can put these charges together, exactly the same charge, okay? But times the two charges, which is 1.6 and 3.2 times 10 to the 19, and 19 is 38. Okay, divided by the distance between them at point A, which is given as 10 to the minus 10 meters. So 10 to the minus 10. So now, if we calculate this, this is now the potential energy at point A is given as 4.61 times 10 to the, okay, minus 18 joules. As you see, we have calculated the potential energy at this point. Okay, now what about the potential energy at point B? The only difference between the two expressions will be just the distance, okay? Twice as much as the distance now, okay, as 10 to the minus 10, 2 times 10 to the minus 10. If you divide this by 2, basically it's just division by 2, okay? It's just 2.30, okay? Then this is just equal to 2.30 something times 10 to the minus 18, right? 18 joules. So this is 18 minus 18 joules. So everything is given. From this, we can calculate the kinetic energy at point B. So from this, kinetic energy at point B is just 1 over 2 times the mass, which is given as 9.11 times 10 to the minus 31 times the kinetic energy, okay, which is given by just 6.41 times 10 to the minus 18, okay, mv square, okay, vb square. This is what we have to find, but this kb is given as just 6.41. If you put all these numbers together, right, these numbers, then this is exactly what we get, times 10 to the minus 18. As you see, all the exponents are 18, so that it's easy just to add them up or subtract. So now from this we can calculate VB, because VB will be the square root of all this, right? VB is equal to square root of, okay, 2 kb divided by m, okay? And now the result is just simply 3.8 times 10 to the 6 meters per second. Now, look, did the speed increase at point B? The answer is yes. It started, the positron started when it is very close to alpha particle. The speed was 3.10 to the 6, but now when it is twice as much as away from this alpha particle, doesn't matter what kind of path it's moving, okay? The speed has increased from 3 to 3.8 meters. So it means that the existence of this alpha particle caused the electron to speed up. If this was an electron, for instance, it would slow down, probably stop somewhere and come back and really stick to this alpha particle, okay? So this is an atomic example that physics teachers and professors love to talk about, but don't forget, this experiment should be done in the vacuum region. So this is extremely important. So only those of the professors who know the physics under this vacuum system will tell you that this experiment should be done in vacuum. Otherwise, we cannot repeat this experiment in the room or something, which is full of the dust and the atoms and the gas particles and everything. So there is no way these atomic particles will move in just regular space other than the vacuum region. Don't forget this. We can reduce the pressures of these vacuum systems to a level which is which has less pressure than the universe. Okay, so this will be the end of 2.5. Okay, and I would like to now ask you if you have some questions.